So this video is about passive RC filters and in particular the first order filters. So we're going to begin by looking at a low pass filter. So with a low pass filter we have a resistor and capacitor in series with the input voltage across the network and the output voltage then just measured across the capacitor. So the basic principle of it is when we have low frequencies, so when F is 0, sorry, maybe not 0, when F is 0.1, we have a small number here, so 1 over a small number is a large number, so we get a large XC. So the majority of the input voltage will be dropped across the capacitor. As the frequency increases, so as frequency increases, the capacitive reactance decreases, and it'll eventually go to a very low number. And when it gets to a very low number, then practically all the voltage then is dropped across the resistor and very little of the voltage is dropped across the capacitor. So that's the basic principle of it. But let's look at an example here using these values. So with these values for R and C, we can put them into this formula here, which gives us the cutoff frequency. So the cutoff frequency is 1 over 2 pi RC. When I do that, I get a value of 1 kilohertz. I then created a table where I went from 10 hertz up to 1 megahertz, and then I got the log value of each of these. So the log of 10 is 1, log of 100 is 2, log of 1,000 is 3, and so on. Then for each frequency, I calculated the capacitive reactance, which is 1 over 2 pi FC. And you can see that at small frequencies, the reactance is high, and at large frequencies, it's low. I then calculated the entire impedance of the network, where Z is equal to R squared plus XC squared. And you can see that that also goes from a high value down to a low value, basically down to the R value towards the end. Having calculated Z, I can calculate I. So if we assume an input voltage of 10 volts, so 10 divided by Z gives me my current I, and then my output voltage would be I multiplied by XC. So I multiplied by XC, which in this case is 10 volts. So we now have the gain of the system. So the gain is the input voltage, it's the output voltage over the input voltage. So 10 volts over 10 volts, which is 1. And then I converted that to a decibel. So you might be wondering, when does the decibel go from 10 to 20? Well, the reason is the power is generally V squared over R. V squared over R. So the output power, we're saying V out squared over R, and the input power is V in squared over R. When the R's are equal, that's going to cancel out. So then we're left with V out over V in to be squared. And then from the rule of logs, that can now become, that 2 can multiply by the 20. So it becomes 20 log 10 V out over V in, which is what we have here. And that's what this value is there. Okay, so when I do that with these values, I can plot them on a graph. Okay, so we have the gain here in decibels, and we have the frequency here in a logarithmic scale. So this is called a Bode plot, B-O-D-E, or some people call it a Bode plot. And we can see that as the frequency increases, the gain begins to fall off. So only these low frequencies will get passed, will get the output. And the cutoff point here, which is 1 kilohertz, is called the half power point. And then at that point, the output is 3 dBs down from the input. So it's down by 3 dBs. So why is it called the half power point? Well, generally, decibels is 10 log to the base 10 of, whatever the gain is. And in this case, V out squared over R or V in squared over R. So if the R's are the same, they'll cancel out. So we're left V out over V in squared. And if I go 1 over root 2 and I square that, that's a half. So that's where this half power point comes from. And 10 times log 10 of a half is 3 dBs. So that's where that point comes from. So if I go back and look at my graph here, there's that half power point. I also want to look at two frequencies in particular, the 10 kilohertz and the 20 kilohertz. So on the logarithmic scale, that's 4 and that's 4.3, and we can see that the gain is minus 20 and minus 26 dB. So there's our half power point, so there's the cutoff frequency, and there's my 10 kilohertz at 10 to the power 4, and there's my 20 kilohertz, which is 10 to the power 4.3. So the frequency has doubled, and we can see that the drop off is 6 dB. So when we're describing this filter, we'd say that the drop off is 6 dBs per octave. So where there's a doubling of frequency, there will be a drop off of 6 dB. So that's the slope of this line here, 6 dBs per octave. The high pass filter is exactly the same principles. It's just we swap the capacitor and resistor places. So now when the frequency is low, so low frequencies, 1 over a low number is a high number. So there'll be a large voltage drop across the capacitor and nothing across the resistor. And then when the frequencies are high, which we want, high pass, at high frequencies, this capacitive reactance will be very low. That'll be 0 nearly. So that all the voltage then get dropped across the resistor, which is what we want. So once again, if we create a table, we have the input frequencies, put them on a log scale, calculate XC and Z and I. This case, the V out will just be I. Instead of being multiplied by XC, it's going to be multiplied by R. So it's I multiplied by R. And then we'll get our gain, and then get the gain in decibel values. And you can see at the low frequencies, there's nothing getting through. And then we come up to the cutoff frequency, which in this case is 1 kilohertz. It's 3 dBs down. And anything above that then, practically all getting through. Okay, so high pass filter. Once again, we'll look at the slope. So we look at 100 hertz and 200 hertz, which is 2 and 2.3. So we look at that on the next graph. So 2 and 2.3. At 2, it was minus 20 dBs. At 200 is minus 14 dBs. So the difference is again 6 dBs. So we have 6 dBs per octave. So with the doubling of the frequency, the gain is changing by 6 dBs. Okay, so I hope that's some use for RC filters.